record this. Today we're going to be going back over time complexity. We're going to be talking about space complexity a little bit, and we are going to be going over um, improving first pass solutions algorithmically. So, got 8 people now. All right, I'm going to go ahead and get started. So, first of all, we're going to recap time complexity yet again. Remember, we talked about the big O, otherwise known as the time complexity or the runtime complexity. Remember that the big thing that we're remembering with time complexity is it's not actually counting time in units of time, in seconds and milliseconds. It is counting the number of operations that are being executed within the block of code that we are examining. So just one thing to I see somebody's typing. There's nothing in this GP that's specifically about permutations. If we have time, we could talk about permutations. Otherwise, that's something that can be brought up in the Q&A. That's the best I can give you on that right now. There's nothing written in planned, but if we do have time, but I'm gonna get moving with this, so hopefully we can have some time at the end to talk about it. I assume that some people are maybe wanting to see that based on the independent project. Going back to time complexity, who can tell me if you access an element of an array, what time is that? O to the whatever, or what's the name of it? You can give me the string name or the big O. Accessing an element in an array with a known index. Yeah, O to the 1. How about if you're searching for an element in an unordered array? O to the C, O to the constant. Yeah, John, the same thing. If you're searching in an unordered array, probably saying you're going to be iterating over that array. You got to iterate over the array with n elements. What is the big N? Big O, excuse me. Yep, O to the N. Because for each new index that you add, that's one more step you have to take when you are iterating over that array. As far as space complexity goes, and we'll kind of loop back around to touch on this, it's the same notation as time complexity, but what space complexity deals with is the amount of memory required. It has nothing to do with how complex the operation is, even though that can directly affect the space complexity, the number of operations. The space complexity is the amount of memory required with an increase in the size of our input. In other words, if we have n amount of input and we have to make a copy of the original data set to perform some operation on it. So remember, kind of like when we were doing the sorting and we had the sort in place where we didn't have to use more memory. And then we had situations where we could blow up the stack because we were using so much memory that we were bypassing the limits of the Python stack. So 2 different considerations. One is looking at the amount of operations being performed Sort of an extension with that, but not to be confused with that, is the actual amount of time it takes to run. Because of course, when you have end users that are looking for a quick turnaround, seconds do matter. So if you had to, the complexity of what I had described, the data set and having to copy over a operation to perform an operation on it, it's a space complexity of O to the N. I'm going to go over a lot of examples. And y'all can kind of participate, and I will just talk through these. I want to move through these fairly quickly, but these are just, I know we didn't have a lot of working examples, but these are a lot of examples of working through complexity. And who can tell me this first piece up here, foo, what the space complexity of it would be? And be careful when you think about this one. I'll just start out because, like I said, we know this is going to be a 1 because this is a simple assignment. It's a single operation going on. Even if there's things going on under the hood, this is constant. What are we going to get for this loop, though? Anybody? Think about the square root is the square root of n. So for this one, you would think n time because it's a, no, not log n, but if you would think n time because it is a loop. So the loop would be the dominant. We would assign this a 1. The loop would be the dominant. It would have an n. The print statement inside the loop is just a 1. That's going to end up getting dropped, and that's all we've got. But the thing you got to remember is, actually, this is square root here that the I runs to. So the max, the O to the N here is actually O square root of N. How about this next one? So how about bar right here? I didn't collapse it. What would be the big O of this? A bar. And a loop. This is just going to be a 1. This is going to be an N. This is going to be an N. Yep, O to the N squared. Because this will simply be a 1 because it's a single operation being performed. The N multiplied by the N squared. How about for the next one right here, Baz?
So I have one question. Are you asked for space complexity or the time complexity?
Well, for all of these, we're going over the time complexity, but it's all the same notation. But these are just going over time complexity.
Okay. Just want to make sure.
Yeah, this is covering time complexity, but they're annotated the same way and they're computed the same way. You're simply computing it in terms of memory for space complexity as opposed to the time complexity is going to be the most important and the most used, but space complexity definitely comes into play and definitely deserves consideration. So this one right here, you would have n, but then in this case, you would actually have square root of n. So the big O of this one would be n square root of n. That would be the final big O for this. How about for this one?
Wait, sorry, for the last one, what was the solution?
And the solution would be n, it would be O to the n square root, however you wanted to denote that, of n. because you have an n here, but this, because it only runs to the square root of n, is square root of n time like we saw in this first problem. So you have n times square root of n. So it's kind of like n log n, but this one's n square root of n.
But what about the second iteration within the other one? Would that not make it squared? Or
What were you asking about? I'm sorry.
I was saying, what about the second iteration within the first one? So line 22. Wouldn't that make it squared? Or am I missing something?
This is asking for the square root of n. So the range is only from, the j is in range from 0 to the square root of n. As n increases, that loop only runs square root of n. The maximum it has to run is not n times, but square root of n times. That's significantly different than n. Do you see what?
Okay.
Because n is our input. Here, this is linear time. This is n time right here. This is n time. Right here, this is actually square root of n time because we're taking the square root here. So it's only running up to the square root. So then this becomes n. Remember, we multiply for loop. So in this case, it's n times square root of n. This is, of course, ignored because it's one time. This assignment is one time. Does that make sense now?
Yeah, yeah.
And how about this one? Going to have line 29 is constant time. Line 31 is n time. Line 32 is 2n time because we have 2 times n. Line 33 is 1 time. So, yeah, and Ilya, what would that turn out to be? 2n to the second power, but what would that be because of the rule that we talked about yesterday of something we always do?
That would just be n squared.
Yep, just the n squared. That's all we're looking for. This one's kind of weird, and I'm just going to talk through it real quick. Anybody want to take a guess at what this one is? You have to look at the whole loop. You've got 3 loops in here, but you got to look at the whole loop and what's going on down here and what's going on with the sum. So as we're taking an n, I is going to run until I is greater than 14. So actually it runs from 0 to 14. I always have to remember if these are inclusive or not, but it runs to 1463 or 1462. And then we have an I plus equals the sum. The sum starts at 0. And we're going to iterate through from 0 to x. So for all practical purposes, this is constant time because this is the most this does is runs 1,463 times. Lots of time, but still not much. This would be n time because it runs from 0 to x. And then this inner loop is going to run from x to x plus 15. So it only runs 15 times. So we could call that for the moment 15, even though what that is that comes out to a 1 again. Does anybody see what this is doing that's weird?
Is that O and log n?
What I tell I'm sorry, I don't think I caught what you were saying. What were you?
Is that the O and log n?
Yeah, it's not n log n. This one actually just turns out, yeah, Esteban's got it. It's just n. Because the problem here is we're looking at, x could either be small or large. When x is small here, this is going to iterate. This is going to iterate, and the sum only increases 15 times. So the sum, I only increments up slowly in this case if x is small. That way this outer loop is able to keep running because the sum here is small. That makes sense? But when x is large, we're running x many times and therefore running k many times, and we're adding to this sum very quickly. So as x gets larger and larger, I think as it approaches about 97 or 98, if my memory is correct, it approaches the point where this outer loop only runs once. We do take the dominating, so this is a 1, this is simply a 1, and this is an n. So this is just n time. Anybody have any questions over that? I know that I had to take a look at this one the first time it went through because I didn't really get what it was doing.
So for me, on 942, I saw that that would be n plus 15 instead just 1.
It's constant time, so it would be it runs a maximum of 15 times. So for all practical purposes, that's constant time. Because remember, we're dropping the non-dominating factor and we're dropping leading coefficients. So whether you have 1 or whether you have 3,000, it disappears. Do you remember what I'm talking about?
Kind of.
This runs from x to x plus 15. Therefore, this only runs 15 times. So it doesn't matter how big or small x is. This only runs 15 times, and each time it runs, it adds 1 to the sum. If x is small, that means this outer loop here, this loop that is outer to this loop, doesn't run many times. Therefore, this doesn't run many times. Therefore, you don't add much to the sum. The sum here stays small, and we stay within the range that's iterating here. It's a lot going on. As x gets bigger, this runs more times.
I see it.
This inner loop runs more times as x increases, thus increasing the sum very quickly, and it reaches a point where the sum actually, I think at 97 or 98, the sum bypasses 1463 in one pass. All you'd have to do is divide 1463 divided by, I think 97, and you would get just divided by 1463 divided by 15 should be about 97. So that's what this one's doing. That it's a weird one, but this one just goes to show. I mean, it's not anything yeah, it's 97.5. So it could you share bar? Do you want me to share all of these?
No. I see what I mean, but I just forgot that on the third one the starting point is x also. I always thought the starting point is 0. Sorry.
Oh no. Okay. Yeah, that's okay. So that's that one. Then this next one we've got the array. I'm just going to run through this one fast because it's simple. It's a lot of stuff, but this is simply one time because you're just printing the first index. Then this is an assignment. This is a 1. This is from 0 to the midpoint. The midpoint is the length divided by 2. So actually this comes out to be 1/2 n, I guess, if you would. This is one time. This is, even though it's printing up to 1,000, what is this? This one time, n time, n log n.
It would be just 1.
It's one time because we've got a leading number. We got one time. We have one time with the comparison. We have another one time. We have n minus 1. So what's I went down into the second one, my bad. So all this comes out to be is a bunch of ones that drop and a 1/2 n. I guess you could call this one 1,000 time, but what does this end up being? This whole Baz. It's just n time because all of these drop, the ones drop, the half drops, the one drops, the one drops, and the one drops. So all you've got is n. And then for a recursive call like we've got here, I know it's kind of, this recursive call is simply going to be n, if you remember. It's got its base case. We're printing n. This is one time. Then we're calling n minus 1. So obviously, if we're starting with n, calling n minus 1 down to 0, if the base case, let's say, was something else where if n is equal to nothing comes up in the top of my mind, but if you set the base case difference, it wouldn't necessarily be n time, but this is n time for basic recursion. For this case, we've got, what would this be? Notice down on line 73 and 74, each time the function calls, it calls itself recursively twice, one with n minus 1, one with n minus 2. This one also has the base case at 0, but each time you call this function, you call this function twice. Then each time you call each of these, then you call this function again and you call it twice. What would the runtime be on this? It's horrible.
And triple thing, I forgot how do I say that. And square. I know it's not n square.
It's n squared.
Is that square?
Yeah.
Oh.
Because this is n times n, the way it's doing it. So each time, because each time you call the function, you increase it by a factor, a power of 2. It's n squared. Does that make sense? Yeah,
Yes, it does make sense.
think about every time this is called, it has to call this twice. Then every time each of these are called, it's calling this again, and it has to call this twice. So it's like a cell massively dividing, and each time n gets greater, it's got to go to the second power because each of these, think of this as n, think of this as n time, because this is n minus 1 and n minus 2. So these are each n time. So it's n times n because it's within the same function. So it's n times n, which is n squared. And then this one I had, sorry, these got all ugly looking with the errors. The name and phone book. What would this one be? Iterating through the phone book is what it's doing here. And what would worst case be here? So what would this case be here? For name and phone book, if name equals to find, we're looking for a name, return true, else return false if we do not find that name at all. Yeah, n time. We're simply iterating through just in a different way. How about this one? This final one. Pay attention to line 97 and line 101. So if the length is 0, we just return false. We pick a middle. This is going to be one time. The middle is just the length of the phone book. And the current is the phone book at that middle index. Phone book's going to be brought in as an array. So we're accessing that array here. if toFind equals current, remember we're looking something, then we simply return true. This is another one time. If toFind, so we're in, if toFind is less than current, return name and phone book, toFind, and then for what we're searching, so this is a recursive call here. But what time is this? Because here, if the name is less than the current, if what we're finding is less than the current, we return from the beginning to the middle. Remember this Python syntax. Otherwise, we return from the middle to the end if it's greater than, if the toFind is greater than the current. Yeah, it's login time, Ilya. It's login time because why? What are we doing here? It's 2 words. Starts with a D, the first word. What are we doing that lets us know this is login time? I know this one isn't easy to see. This is another one it took me a minute to look at it to figure out why it was what it is. We're dividing and conquering.
Yeah, it looks just like the binary. What is it? Binary search?
It is. It's a binary search, and I
Yeah.
was happy someone said that because I intentionally didn't say it. But yeah, it's a binary search. It's just a nifty little way of writing that they've done with this syntax and whatnot. So, were there any large questions about this? I'll drop all of these. I don't have the answers or anything in there, but good to look over. All right, so there's that code. I'm going to jump to something that talks about space complexity, and this is just an outside link. I can give you a link to it. It's not written in a language that we usually use, if anyone wants this link, but it's a good talk about space complexity and some examples of it. So you can read through all the text if you want, but remember with space complexity that we're counting how much memory a change in the input size results in. So for this first one, you're taking in 3 arguments and then you're making an assignment based on those 3 arguments. So what it's saying here is this requires a unit of space, this requires a unit of space, this requires a unit of space, and then this will also require a unit of space. This is an operation, but the unit of space has to be allocated for R, and then we're returning R. So we're having to allocate 4 units of space. Now we remember that space complexity is computed the same way as time complexity, so we simply drop that 4 to become a 1, and this is O of 1 time. Reason being, no matter what we do to these inputs, no matter what we make these integers, it doesn't matter how large we make them, they still are running a single operation. Does that make sense to everybody? How about this one right here? So we got an operation here that, like I said, don't pay attention to the particular syntax because this is not written in Python, not written in JavaScript, but you're taking in an array, you're taking in an integer n. We initialize r at 0, so that's 1 time. And we're going to say, let's iterate from 0 up to n, whatever n we supply, and then we'll increment the I. And then you're just going to take r, this sum here, and plus equal it to the value at that index. So the bigger n, the longer this has to run. Who can tell me what time that's going to be? I know it's written right there, but does everybody see why? It's n time in here, as it says down here, because it needs n units for A being this array.
It will create new item every time it loops.
What's that?
Because it's creating new item every time the for loop runs until n.
I'm sorry, I don't understand what your question is.
I know it's not a question. You asked why it's n.
Yeah.
That it's going to create a new item in the memory and needs to allocate memory.
So we have O to the n time here. Like I said, I dropped a link here, but without spending too much time going over it, you're going to calculate the space complexity the same way you do the time complexity, but you're just going to have to take into consideration the memory that is being allocated as a result of it. So if no additional memory has to be allocated, no matter what the input is, it's a constant time. If you're having to make a copy of the data, and obviously every time you increase a unit, you're going to get it, you have to make one more unit of space for that data that's being copied over. It doesn't matter even the size in bytes or whatever. We'll just think of it in terms of one more unit of space that you have to copy over. So that is n time as far as space complexity. We know that in a recursive call, I don't think they show that here, but if you had a recursive call, what's the space complexity in a simple recursive call? In a simple recursive call, what is the space complexity? Anybody? In a simple recursive call, where the function starts out at n and it decrements n by 1 each time, and at the end, all it's doing is, as it decrements n by 1, it's printing n. But what's the space complexity of that recursive call? Yeah, it's n. Because every time that you call that function, remember, with recursion can operate. It can call the function, which calls a function, which then calls itself, which calls itself, and this can all occur simultaneously. So each time you're calling the function, you're having to create a new space in memory. Yes, you're still running the same amount of operations, but because they're running simultaneously, you're adding additional spaces in memory. Does that make sense? And actually, they do touch on that down here. If A calls itself recursively n times, it can't be reused because every call is still in product. And I actually misspoke when I said yes, it's the n squared, because you have a function calling a function. And then this gets down into talking here is something that doesn't apply right now. It talks about pointing by reference or by pointer. which we will cover more in C. And we did briefly go over when we were talking about an introduction to Python about reference versus value and passing arguments. I'm going to make a thing. I've talked a lot. I just want to ask, are there any questions? Make it anonymous, and you can just post the questions in the thing, or click no if you don't have any questions. Anything that we've covered today about going back over time complexity, anything with recursion that we've talked about again, anything with the space complexity that we've introduced, any of the problems that we've gone over, any of the theoretical things I've asked, like what people answer the, all right, answer the poll or type your question out. While I'm waiting, I'm going to go ahead and take attendance. Does every recursive function call need memory allocation? Yes, it does. And think about it this way, and this is why. Think about when you iterate through a loop. That loop, it's happening under the hood in the languages that we're using. We'll see it happen where you actually have to take control of it in C. But each time that you say you're going to run from 1 to 1,000, that loop is constantly running. So you run the loop, and then you run the loop again, then you run the loop again, then you run the loop again. Each time you run the loop, you free up the memory that you used running the operations in that previous loop. And this is one of the reasons we were talking the other day that iterative solutions do not necessarily fall into the category as inferior to recursive solutions, because the problem you see with space complexity with a recursive function is, remember, the function is calling itself, and we talked about it going down as a tree and then bubbling back up like an inverted tree as it trickles down, and that function keeps calling itself, and then as it returns and bubbles back up, you get to that final return. But that all happens simultaneously, so each time you run the function, you have to save another place in memory, let's say, for whatever's being run inside of that, whatever operation is being run. So new places in memory. It doesn't matter the actual bytes that are going to be created, but we have that memory that has to be accounted for. Does that make sense? You can type up under the comment. Because every recursive call needs memory allocation. That's why we see that stack blown up, that number of 3,000 that came out, or 1,000 like we were seeing the other day, why you can blow up your stack in a recursive call, because it's the memory. Okay. I'm assuming nobody else has anything because nothing has shown up here. I'm going to give you a 5-minute break, come back at 7 after the hour. Actually, just come back at the hour. When we come back at the hour, we will jump into coding, and we will code the rest of the time. So come back at the hour, and I will pause the share right now. Everybody should be getting back in, and we'll get started in about 2 minutes. All right, I'm going to go ahead and get started in 1 minute on the hour. So everybody get settled back in, get ready to go. All right, I'm going to go ahead and get started again. So hopefully everybody's back in. We are going to go through problem solving again and working through algorithms. So the problem I'm going to give you, and I'm going to do this partially interactive, and I'm going to do some of it just coding and talking, but I'm going to try to make it as interactive as I can. So you're going to get a text file for your problem that we're going to work through. You're going to get a text file. This text file actually exists. It's sitting on my desktop. And this text file has a lot of random words in it. Given this text file, you're going to print out the largest set of anagrams using the Python language. So you're going to get a word.txt file. You're going to take those words and print out the largest set of anagrams. What are some questions? First thing, what we got to understand the problem. So what are some questions that may come up? Talk or get on or type or something.
What's an anagram?
Yeah, Ron, that's a good idea, how to open the TXT file. I've got the stuff written over here, but we can talk through this a little bit when we run these solutions or some of these solutions. But yeah, how do you open the text file and read the text file? And we will deal with that right here later on. And someone said, what's an anagram? So an anagram is a word, phrase, or name formed by rearranging the letters of another. So for example, if you had spar and you had rasp, the letters within these two words can be rearranged to be the other. Rasp can be the SP, the A, and the R can be taken to form spar. So these are anagrams. And then if you had another one that was PARS, that's also part of this set because all these are anagrams because the letters in each one can be rearranged to the letters in the other. So good questions. What's an anagram? That's probably the key question here. And then also the text file that you're talking about is important, how we're going to actually open that and feed everything through. And that's kind of happened behind the scenes for us with the tests that I've already got here. But like I said, we can talk about them. So if we're going to work for a first pass solution, just get a quick solution, not have to think this out too much. How would we go about maybe solving this? What would we have to maybe do? What would be the brute force method of Fig doing this? That's what we're going to aim towards for this first solution. What would be the brute force method to do this? We're trying to find out what the largest set of anagrams is. We have a word file that we will be reading in. What's the brute force way to do this? Somebody talk. Got to find the largest. I heard someone undo their mic.
John, in your text file, what does it contain? Just a bunch of words in like an array or something? Or?
Yeah, don't just know that you'll get a bunch. You'll get a bunch of text words out of the text file. Yeah, don't overthink the text file itself. Assume that you will be able to read through you'll be able to access this file, and for every word in there, you're going to read the word in and you're going to have access to it. So you've got to go, what I'm looking for here is that the dirty solution, the first pass solution here would simply be to generate every possible set of anagrams and then simply say which one's the longest. Does that make sense? And there's obviously more efficient ways of doing this that you can already be thinking about and that we'll cover the next. But if we were just going to try to implement this, we could call this first pass anagrams, and it takes in words. Now understand that it's taking in words from right here, okay? It's reading in those words and it's splitting them where there's a new line, because that's how the file's set up, where there's just there's a new line after each word. So it's just taking those words, reading them in, setting that variable. That list that we're going to end up with. So we can say we're taking in those words. We're going to import, and we'll see why, random, and import the operator. And how we're going to go about doing this, how would we figure out, what would be a way that you might think of that we could figure out if we had an anagram? What would be, as we're iterating through all these possible, as we're creating these anagrams, how would we maybe decide if a particular word was an anagram? Because
all the characters should equal.
All the characters should equal. So then what would you make? What could be something we could do to determine if two words contain the same characters, but not necessarily in the same order? In fact, not in the same order. What could we maybe do? What I'm thinking maybe we could do here is we could assign each letter a numeric value. And then from that numeric value, we get a total value for each word. And if the values match for each word, RASP and SPAR, obviously, if we had assigned a numeric value to RA, S, and P, or SP, A, and R, the same letters, sum them together. If the sums were equal, the integer sums were equal, then they're an anagram. Does that make sense? So we could just say, we could use this fancy syntax and fill an array of zeros times 26. This is just making an array of zeros at this point. Then we could just say for I in range 26, remember this actually runs from, now this will run from 0 to 25. The range is not inclusive. So we have, this creates an array of 26 zeros at the indices. This is iterating over that array. And we're going to say characters at I, the I that's going from 0 to 25, equals random dot rand int. That's why we imported the random. And we'll say between 0, 100,000. So So all we're doing here is we're creating an A, and it's going to pick a random number between 1 and 1 million to assign to it. B is going to be 0, the first index. A is the 0 index. B is the first. So we're making a random numerical representation per pass of this function each time the function works. Remember, the function's only got to run one time total. So in this one time, we're giving it a value, and then we can take these values. We'll create a new dictionary. Remember, that's the same as an object. And we will make what we'll call a signature, and the signature is going to be that total that we will look for. So now that we've got this in place where we have a value assigned to each letter, and we've got our variables declared and set up, our anagrams, our signature, what would we need to do now? Somebody talk. What would we need to do now that we've got this in place?
Loop through words and assign every character. Get sum of every character.
You mean like get the values that we did up here, get the sum? Yeah. So we could say for char in Word, index equals ord char minus 97. Does anybody know what line 13 is doing? And actually before this, in an outer loop, we will say for word in words, and this might become more apparent why we do this. We will say word equals word. So we've read in these words. Now we're going to make them all lowercase, and this will make the entire word lowercase. The reason we're doing that is we're going to use Unicode. If you're not aware of what Unicode is, it's basically an international standard for characters that appear, and there's a numerical value for each of those. So the uppercase letters have a different value than lowercase. So since we're not going to pay attention to casing here, which could have been another question in the planning stage or a question to ask, hey, are we going to pay attention to case? But we won't be paying attention to that here. So we can make it all lowercase. Then for each character in each word, as we go over each letter, we're simply going to say the index equals, we're putting in a character, and this ord is a built-in function for Python. It will simply return the Unicode value. Then to line it up with this, the 0 through 26, we will simply subtract 97 from the Unicode value because those letters fall in that range there, starting at the upper 90s and going into the hundreds for the lowercase. You can look those up. Remember the uppercase, I think, run from the low high 60s to the 80s, if I'm not mistaken. So you're getting that number, and then we will say we've got an index. If index is greater than or equal to 0 and index is less than 26, what are we doing here? What are we doing? Somebody type or speak. We've gotten this index. Now, why are we going to see if it's between 0 and... No, you don't have to sort each word, John, but that's actually another approach that is much more efficient that we'll see here shortly. This is simply passing through each word. It doesn't matter which order that the characters are in, because it's going to get the value for that specific character, and it's going to add to that signature that we're about to add to. We will just say signature plus equals cars at index, the value that we assigned it up here, that random number. So we're going through and taking each letter, saying what's the value that we randomly generated for that letter, add that to the signature at the very end, we have a signature. And if that signature, that numerical value is ever the same, we knew it contained all of the letters. Does that make sense, John? But the problem is we're having to go through each word and iterate through each character and then make the comparisons that we're about to make. So we're going to look now, and we can say, trying to see where I've made an error here that it's. Try to retype this. An index is greater than or equal to 0 and index is less than 25. Then we will say signature like we talked about, plus equals characters at the index. And then we can come back out. Give me 1 second to make sure I've got all this right. Anybody see why this is throwing an error here?
16, does it need one more space before the index?
Ah, good catch. And then that sits. Thank you. And these are things that happened. And I should have noticed that with that extension that I've got in there, but thank you for catching that. So we're iterating over each word. We're making them lowercase. We're going through each character in each word. We're giving it a value between 0 and 25, the same as we did up here. That corresponds with A to Z. We're then checking if that value, if we indeed have encountered a lowercase letter. So this will eliminate any periods or forward slashes or ats or whatever else may be in there theoretically. We add to the signature, the index, that value that we did up here. And then we can say, here, if signature, the signature just being that index, the key, not in anagrams, signature, and we will just make a new key and a value. The value that we will initialize is an empty. Remember, we're dealing with a dictionary, the same as an object. So we're making a new key value pair and simply saying that the signature, we're going to make it an integer, the anagrams and the signature, this comes up with the signature that we computed here. So we make for that a new empty. And if it's already there, it will just bypass this step. And we will say anagrams at the signature. So that accesses that specific dot append. I can type, and we will append the word. And then we're going to say signature equals 0 because it's got to loop back around again. And then we can say, this is a line that you could ask in the Q&A about, or maybe if someone here knows the exact Python. I remember this before, and I ended up asking one of the instructors, and they didn't know exactly what it was doing, but this is a Pythonic way using some built-in functions to find which anagram is the longest. Max anagrams equals max anagrams dot items. Key equals operator dot item getter 1 and 0, and we imported the operator. So this needs to be indented 1, and that should make everything go away because it was treating it like it was outside the function. And then we will print the max anagrams, and that will simply print out everything that is in that list. And this code should run. Does anyone have any questions over what we did here? All right. And then before this, we need to import time. So all this is doing is this is opening up this txt file. And you don't even need this. This is just the default. And then we're just saying the words, and we're reading that text file, splitting it at the new line, and adding this to the words, and then f.close. So we need to import time for that, because here we're going to do time.time. We're going to run first pass anagrams with words that we did here, this list of words that we created, and then we're going to print the end time versus the start time, and those are simply done by calling time.time. This operation, when it completes, we call the time again, subtract this from this, and we get the time in seconds. So all of this should work if I try to run it right now. And I can say Python 3 algos.py. Operator.item getter is not, object is not subscriptable.
So the parentheses on the 1.
Where
After line 27, after key equals operator.item getter, the parentheses on the 1 have to be brackets. But
I missed.
Yeah, I've never seen this particular usage before, though.
Yeah, I don't really know. I don't really know how it's working. That's why I said I asked one of the instructors about this line before, I'm remembering, and they didn't know how it's working. What it is doing is it's bringing in that operator, and it is picking the longest list.
Nice.
How it did, I think, well, it's saying, okay,
Anagrams to items. Anagrams to items.
anagrams.items. And so it's going through each, and then it's just saying the max, and then giving the key is the operator.item giver at 1. And then it's taking the max of all that.
So anagrams.items returns the keys and the values from the anagrams dictionary.
Right. And then how does it get? It's picking the max out of the keys and the item. So it has to pick the max from the value, the maximum values.
Right.
Which array is longer? Which list is longer?
So the parentheses around the 1 after key equals operator to item getter, those have to be brackets. But I'm not sure which.
This is the correct syntax right here, I think. Let me try again.
Because the type error is coming back not subscriptable. Oh, I see what you're saying. Okay.
Now it does it. There's a first pass runtime of 0.86 seconds. I don't know what this does right here. That's the key of what I don't know what it's getting, what it's doing. But that's something you can ask in GP. I'm going to keep on moving, but you can see how this problem, like I said, what we did is we made a setup so that we could give each letter an index representation, 0 to 25, A to Z. We assigned it a random int. We made a dictionary and a signature. We iterate through all the words and make them lowercase so we can use the Unicode because we're not going to deal with uppercase. We find out what the Unicode value is. We check to make sure it's within the range that we have now created for lowercase letters since we subtracted 97. We have, instead of being 97 to 123 or whatnot, it's going to be 0 to 26 or 0 to 25. Then it just adds the signature, which is to the signature, the value that we have created randomly here. We're checking if that specific numeric signature is in anagrams as a key. If it's not, we will say anagrams at that key equals an empty array. So you're simply making a new key value pair. Then no matter what the case is, you're going to append the word, the actual word, not the sorted word. This will take, remember, this started out for word and word. So this is the actual word. We reset the signature to 0, and we do this for everything. We print the max in the end, but before that, we ran this line that we're not quite sure what this little part was doing here, but it gets the max in an efficient way. Here we just import the time, get a start time and end time, invoking our first pass. And here we're just opening the file, reading through the file, and splitting each word and putting it into words, which is a list of all the words that we're creating. Then we simply close the file, and we use that right here when we call first pass anagrams. Remember, that takes in words. So somebody said it. I'm going to give everybody about a 2-minute break because I want to grab a glass of water. Somebody said it, though, so be typing, what can we do to improve this? Well, we're not having to iterate over every word, and we're not having to iterate over every character. And what can we possibly do to improve this? Be thinking about that, and I'll be right back. All right, we're going to get started again. Somebody had mentioned earlier something, and they mentioned sorting the words. So if we sorted the words, remember it does not sort alphabetically, but it will sort them based on their Unicode. So if you sort anagrams, what you would end up with is it would be alphabetized because of the 1 through 26, but you would sort each of the letters. So that would be the next approach that we could take. So if we wanted to define a second pass solution, I'm going to do the same and take in words. I'm going to make a new dictionary first thing. We're going to set a variable longest for the anagrams. Now we need to generate every set of anagrams, so we will say for word and words. And so we have a list and we need to turn that into a string. Remember, we're going over each word in the words. So if we wanted to get that signature that we did last time, we'll say signature and we'll say string, join, sorted, word, dot lower. And that should be correct. And then if the signature is not in anagrams, we do the same as below and say the signature equals a new set. Regardless, we say anagrams, signature, dot append, and the word. So once again, we're still using the word, not we'll have the actual word come back to us. Not what we did here is for each word, we're going to once again iterate over each word, but we're going to get that signature all here. We're going to say a string. We're just taking a string. Remember the signature. It's going to be in a string this time around. And we're simply joining when we I guess it's easier here to work from the inside out. We say word dot lower, so we're going to bring this all to lowercase. Then we say sorted. What this is going to do, this is a built-in Python function, sorting function. It will sort it by letters, by Unicode. So it'll take these lowercase words and it'll sort the letter based on what is the greater Unicode on the letter. It gives you a result in an array. So just like in JavaScript, we're having to say dot join to get that. So all this is doing right here is taking the word and sorting it and joining it back together so that you have the word. Then the signature, therefore, becomes that word that's been sorted. So we look to see is that same signature, let's say for spar, remember we had spar and rasp. The signature for this would be A, P, R, S. So we're going to say, is that already in this dictionary? If it's not, you're going to make a new array for it. And regardless whether you made a new list or not, you're going to append to that signature in that dictionary this new word. And then to test it, all we're going to do is say if longest equals none, in other words, if nothing's even been assigned to it, or the length of anagrams at signature greater than the length of what we currently have as the longest. We will say longest equals signature. So all we're doing right there is we're going to say if it hasn't been assigned a value, we've been through and we've got this first signature. If it hasn't been assigned a value, or if the length of the current signature, remember the current signature is greater than the length of the longest signature that we have previously set or are setting here, then we reset the longest to the signature. So it's just looking to see which is what has a longer length, what has more indices, what has more elements, reassigning longest if it's necessary, if the current signature is greater than what the longest signature already in memory is. And then you can simply come back out to here and say print anagrams longest, and that should be that. And I'm going to look at anagrams longest for word and words. Signature not, add it. Add the signature, the word, the longest equals none or length. Anagram signature, length, anagram longest. Okay, so we should be able to run this second piece of code as well. We can go in here into the command line, invoke that. We get a first pass and we get a second pass. And remember on the second pass, we said to print it. So notice what the output is. ANGOR, Angor, Argon, ANGOR, Goran, ANGOR. It's picked out all these anagrams and it ignores the uppercase. I'm going to make a poll. See what. Anybody have any questions over the second pass solution? What we've done is instead of, now remember, there will be some cost in operations assorted with the sorting, and there will also be space complexity associated with that. But in sorting the word, we don't have to sit there and with our own operation go through each character, then assign each character a numerical value, and getting a sum of that character. We're simply rearranging it and skipping a lot of those inside operations. We're going to rearrange it. Any anagram will rearrange to the same lowercase word and using that for the signature and then keeping our list there. So we're keeping a list. The first time around, we're having to compute a numeric signature. This time around, we're just rearranging the words, which we had to iterate over the characters anyways. And now we've got a signature without having to keep that running total, without having to generate the random numbers up top. So operationally, this is more efficient this time around. I'm going to send this to the channel and see if anybody has any questions. No. Come on, everybody answer. If you got any questions, let me know now. All right. And then for the last solution, can anybody think of something that would be even more efficient? And it's going to be a change in the largest set, and actually how we're determining what's the largest set of the anagrams. We're going to go ahead and sort it, but what could we do here if we took this function over and we call this third pass anagrams. And for the third pass anagram, we're going to do this a different way. So everything else is the same. We're creating our dictionary after we take in the words that have been extracted from the file. We iterate over the words. We convert the list to a string. We're going to sort the word, join it back together, because the sort gives, just like the JavaScript, it gives, when you do something, it splits on and it splits it into an array, the return. Then we're going to join that as a string. We look for the signature if it already exists. If it does not, we create a new array for it. We append the word to that array. At the end, we print the longest. So we're doing the same thing that we were doing in the first operation, but the difference is we could slightly improve this if we went down and just said max length equals 0, max anagrams equals this, and then we would just say for signature and anagrams, if length of anagrams at the signature is greater than max length equals the length of the anagrams at the signature, and the max anagrams, which is the actual list of the words, equals anagrams at that signature. We got a typo there. So all we're doing here is, after we have made all of our anagrams, we are going to simply go for signature and anagram. So we're going to iterate over each key. And if we're saying if the length of anagrams at that signature is greater than the max length now is the length of the anagrams at this new signature, what we've seen. If this is greater, we simply reassign the max. The max length is originally 0, so whatever passes through first is going to take it on, and then it's just comparing it. And we're just doing, and then the max anagrams is the anagrams at that signature, because that shows the actual list with the anagrams. So it's just a way, instead of keeping track within this for loop, at the very, very end, all we go through here and do is we get all of our sorted anagrams, and then at the very end, we just check the length of each one, and we're not working within the loop like we did this last time, where every time we loop over, we check to see if it's the longest. Same here in the first pass. So we should be able to run this as well. We can save this. First pass, second.
I think you need to remove line 49 and 58.
What did I do here? You're saying 49?
Yeah, you don't use longest anymore.
Yeah.
And you also have on the line.
Yeah, we're going to print max anagrams here. We're solving for max anagrams. And then at the end, we can just print max anagrams.
So you declare the max anagrams after the printing it.
Oh, I put that in the wrong spot. I think I just was typing in the wrong spot. It's a long day. Because there I had it down here. This should work. So we're making a dictionary. We're sorting each word. We're looking for a signature. We're appending it no matter whether it's there or not. If we're all done with that, we set a max length, max anagrams. We iterate over each signature. If the length of that is greater than the maximum length, then the maximum becomes the signature. And then we are simply printing the list. So this should there we go. Anybody want this code?
Yes,
Yes,
please.
please.
Yeah, I'm going to drop it in the. I'll also drop the. Here's the code. I'll also drop the Word file, the text file. Does anybody have any additional questions? Today you've got the other half of your repo. And don't forget the 20-minute rule. I'm going to drop this Word file right now, the words.txt. I am going to zip that real quick. And then I will drop that in the channel as well. So there's the code, there's the text file that's associated with it. Remember, you just have to have those both in the same directory for them to be able to run. If nobody has anything else and doesn't have any questions that they want to put forward, we're running about 13 minutes before the hour, so go ahead and take your lunch. Get back to work on your repo. Remember to push up often. Ask for help when you need help. Reach out to your PMs, the TAs, the help channel, the instructor hour, the after hours, all of it. So I will let everyone go. I will get the people's attendance turned in for those that aren't in my PM group to the other appropriate people, and we will see you later today.
Thank you, John.
Thank you.
Thank you.
Yeah, thank you.